Am I audible? Hello.
Yeah, ma'am,
Yes,
you're
ma'am.
audible.
Yes,
Okay. So you just wait for 5 minutes, then I will start your class. Okay.
ma'am, you are not audible.
Yeah. So let's just start. I think it's 8:10 now. Okay. So you guys know what is the Descartes algorithm, right? Vishal sir have discussed in the last session, maybe. Right? So so in Descartes algorithm, what we will do, our main goal is to find the shortest distance. But here, which graph we will take? So we will take that the weight on the edges will be all the positive numbers or positive weight. Those graphs only, Descartes algorithm can only effectively work on those graph which have those weighted graph mainly, which has a positive weight on every edge. So in this, in today's class, we will start with what we call the Bellman-Ford algorithm, which actually deal with those graphs which has a negative weight on their edges. For example, this type of graph. Suppose this is your some cyclic graph of 4h. Here I'll assigning a weight on this edge to be 1, -1, -2, 3. So in this situation, what we can say about the shortest distance between from a fixed vertex to the other vertices. Okay. So in a graph, if we have negative weight on some edge, then the shortest path, this term is valid only when we don't have negative cycles. What do I mean by negative cycle? Suppose you have such type of graph. Suppose this is your graph, and I'm assigning weight to those three edges to be -1, -3, and 2. Then the total weight of this cycle will be 2, -3, -1, which is again -2. So that means this is a cycle of negative weight, right? So in this case, what happened if I want to find the minimum distance between these two vertices? Let's name them 1 and 2. So if I want to find the minimum distance between these two vertices, yeah. Am I audible?
Yes, ma'am.
Yeah, I just started. I will describe all thing. Okay. So what I'm saying, I'm introducing we mean by a negative cycle. So basically, in a weighted graph, a negative cycle is a cycle which has negative weight. For example, this is a cycle. If you move around these vertices, suppose I'll name it 3, 4, 5, then the cycle 3, 4, 5 had weight -2. So that means this type of cycle is known as the negative cycle. So if we have any weighted graph, suppose this is my graph, I'm naming the vertices 1, 2, 3, 4, 5, 6, and 7. And I'm assigning the weight to be, let's suppose this is 1, 2, 4, and 6. Okay. Then in this weighted graph, I have a negative cycle. So that means I have a cycle which has weight negative numbers, supposingly -2. Okay. So then if I want to find the minimum distance from suppose the vertex 1 from the vertex 1 to a vertex 6, then what can I do? I'll move around this cycle. I mean, you can easily see that if we go from 1 to 2 and then from 2 to 6, what will be our weight of this path? So the weight of this path will be simply 1 plus 6, which is 7, right? This much you understand, right? I'm just following this path. Okay, so the weight of this path will be 7. But what I'll do, so I'm also assigning this edge to be weight, let's say my 1 again. Okay, so what I can do, I'll just follow, instead of this path, I'll follow this path. That first I'll start from 1, I'll go to 2, then I'll go to 3, then I go to 4, 5, and then I come back to 3. Okay, instead of 3, what you can do, we can join them, because that will be much better. Okay, fine. Let's suppose we are joining this way. Okay. So suppose this edge has weight 1 and this edge has weight 5. So what I'll do, so I'll start from 1, go to 2, then go to, now we can easily go to 3. And then from 3, I will follow the path from 4 to 5. And then I'll return back to 2 and via 6. Okay. That is from 1 to 3 to 4 to 5. That go to 2 and then go to 6. Now this is a valid path from 1 to 6, right? Now what is the weight of this path? The weight of this path simply that I have to add those all the weights including the edges, right? So it's simply 1 plus -3 plus -1 plus 2 plus, here it is 5, and then plus 6. Okay, so in case of this is -3, let's suppose this is -30, then what will happen? So then the weight of this path will be, simply you can calculate, it will be some negative quantity, right? So in one case I am getting a weight to be positive one, and in the other case I am getting the weight to be negative one. And this you can this situation can happen for every vertex. If you want to travel from one vertex to another vertex, you can uh, just go into cycle, and you can reduce your weight with weight of the path, and you can get the shortest path in terms of weight. So in general, what we say that the shortest distance of a path in any weighted graph which contain negative cycle is not well defined. This problem is not well defined when we have a weighted graph which has negative cycle. Shortest path problem is not well defined in a negative cycle weighted. So the main point for explaining this example is that if you have a weighted graph which contain a negative cycle, then you cannot talk about the shortest path between any two vertices. Okay. So for that, if we now suppose I have a graph which is a weighted graph and which contains some negative weights on some edges. So then in this graph, how could you find the shortest path between any from a fixed vertex to another vertices? Okay. So for dealing with this problem, we'll use what we call the Benjamin Bellman-Ford algorithm, which is basically the extension of Descartes' algorithm. The process will be similar, but in this algorithm, you have to take more steps irrespective of Descartes' algorithm, because Descartes' algorithm, what we'll do, we'll just start with a vertex and try to find out that, I mean, onto which vertex we reach first. We'll take that vertex and then move away, right? So, but in this algorithm, we have to use, we have to deal in that number of steps will be equal to the number of vertices. Okay, so let's Bellman Ford algorithm. So here, let's suppose I'm denoting this dj will be the minimum distance from whatever vertex we'll fix. Let's suppose I'll fix vertex v, because here we are dealing with what we call the single source shortest path. That means I'm first fixing a vertex and then I have to find what are the shortest path to the remaining vertices. So that's why let's suppose I'll fix my vertex to be v. Then I'll denoting dj will be the minimum distance from vertex v to the vertex j. Okay, so in this algorithm, the process will goes using this formula that your dj will be equals to 0 if you first start with j to be 0, or yeah, initially we will start with j to be 0, and initially we will say that the distance of every vertex will be infinity otherwise, right? And then we'll move using the we'll move inductively as we reach to other vertices. So that means that for each vertex j belongs to our set, let's suppose I have n vertices. So if my vertex j belongs to the set 0 to n minus 1, and if I have edge between j and k, so that means if my pair j comma k belongs to the edge, then I'll say that the distance of dk will nothing but the minimum of distance of dk, or or the distance of dj plus whatever weight that this edge will contain, the weight of j comma k. Okay, so it seems so abstract, but I'll explain using the example, then it will be more clear. Okay. Suppose this is your weighted graph. And you want to find the distance, find the shortest distance from the vertex 0, from 0 to every other vertex. And this graph is a negative weighted graph because there are some edges which contain the negative weight. For example, there is an edge between 1 to 4 and it has weight -1, right? So in this graph, if I want to find the shortest distance from 0 to every other vertex, then how we can apply the algorithm? Okay. So this algorithm works in suppose you have n vertices, then you have to do n steps to find out your shortest path, shortest distance from vertex 0 to every other vertex. So for that, we'll use the table. So in this table, the first row will contain the initials. I mean 0, 1, 2, 3, and 4, because here we have just 5 vertices. And similarly, my rows is also just like the adjacency matrix, whatever we have done, right? Okay. So what I'll do, so these are my steps, okay? So I have to go, I mean 0, 1, 2, 3 basically does not denote the vertices. These are actually the steps. So you can say this is a first step, second step, that will be more clear, third step, fourth and fifth, because we have to do n number of steps if we have n vertices. Okay, so from the first step, what I'll do, so I have to start with 0. So the distance between 0 to 0 is obviously 0 because we are initiating our algorithm from 0, right? Okay, now the distance between 0 to 1 is given to be 1, so I'll update it to be 1. I mean, in the first step I'll take to be infinity all, and in the second step I'll apply the distance whatever the weighted graph says to us. Okay, so in the second steps, there's distance between 0 to 0 is again 0, but the distance between 0 to 1 will become 1. Similarly, distance between 0 to 2, since there is no incoming edge, I cannot move in this direction. So the distance between 0 to 2 is not directly clear that how can, I mean how we can use it. So what we'll do, so we'll use this formula that we know that this distance of k is basically the minimum of distance of j and the distance of j plus the weight of h j comma k. Okay, so here I want to find what is the distance of 1. So the distance of 1 will be, since there is an edge between 0 to 1, so you can say that the minimum of distance of 0 plus distance of 0 plus weight of j comma k. But since we are in the first step, so what I'll do, so I won't consider it. So I'll just consider this quantity. So the distance between 0 to 1 will be 1. Now, from 0, we cannot go to 2, obviously, because there is no edge connecting to from 0 to 2. So in the second step, I'll update the value of, update the distance between 0 to 2, simply infinity. And similar thing can happen for all the other vertices, as there is no edge between 0 to any other vertex. So that's why we can append our distance to be infinity.
Ma'am,
Is this clear or I'm confusing you just? You guys are not saying anything.
ma'am,
Yeah.
which vertex we have to take J and which one K?
Yeah, I think you guys are not, I mean, you guys know what is the discard algorithm, right?
Yeah, yes, ma'am.
Okay, so let's start with the familiar example. This is not clear, right? I mean, no one is saying anything.
Yeah, ma'am, yeah, minimum thing is not, I'm not getting.
Sorry, what?
The algorithm used for minimum.
That we don't understand which one is J, which
Yeah,
vertex is K.
okay, fine. So I'll take some other example or some other approach. Just 1 minute. I'll take other graph. That one which used in lecture. Am I audible now?
Yes.
Okay. So the algorithm start with, suppose I have the similar graph. I have this graph. Okay. So first what you'll do, so you'll obviously we are dealing with the what we call single source shortest path problem. So first we have to fix our vertex, that from which vertex I want to find the minimum distance of other vertex, right? So first I'll fix my 0, and whatever vertex you will fix, that vertex have shortest distance to be assumed to be 0. This is the distance of 0, d0. Okay, so dk basically means the distance of k from the vertex 0. Okay, so the algorithm work with using this formula, that if suppose I have vertex set v to be, in this case I have vertex set v to be 1, 2, 3 and 4, right? So the algorithm basically work on a single formula, that if you have that for each j comma k belongs to E, so that means if you have an h from j to k, this h denote the j to k h. In this example, I have an h from 1 to 4, right? So it simply says that if you have an h j to k from j to k in any weighted graph, then the distance of k you simply update it with this quantity, that it will be the minimum of distance of j comma the distance of j plus whatever the weight this h contain, because this is an weighted h, right? So there will be some weight append on this h, right? So whatever weight this h contain. Okay, so this is a basic formula on which this algorithm work. So we'll try to apply this formula, and here is the thing, that we have to apply this formula in the number of in n number of steps. If you have n vertices, then you have to do this what we can say appending the distance n number of times. So at the end, at the nth step, we get our answer. So in this case, I have 5 vertices, so that means I have to work 5 times, right? So at the fifth time, whatever the weight, whatever the weights we get, that will be our shortest weight, shortest distance weight between the vertex 0 to any other vertex. Okay, so let's form the table. So suppose this is 0, 1, 2, 3, 4, and here I'm dealing with n number of steps. Okay, so in the first steps, I'm saying that my initial point is 0, so I'll take this distance to be 0, and all other vertices at infinite distance. I mean, I don't know what are the distance between any other vertices. So this is the first step we always do. Okay, so in the second step, I'll try to apply this what we can say, this formula, dk formula. Okay, so in the second step, I know that there is only one incoming edge or only one edge between 0 to 1. Okay, so that's why I append the distance between 0 to 1 to be 1, and all other things I'll stay, the all other infinities will stay as it is, because there is no edge from 0 to any other vertex. Okay, so in the second step we'll assign, so you can simply say that in second step we'll assign the weight to the neighbor of 0, be precise. Okay, so this will be your weight in the second step. Okay, so in this third step, what we'll do, so we'll try to use this formula. Since we have distance now, so I want to find what is the distance of 0 in second step also. So initially the distance of 0 will remain 0 in every step, because 0 is our starting vertex. Okay, and if I want to find out the distance of 1 now, so what we can do, so we can apply this formula, but as we know the distance of j is 0, so we cannot consider that the minimum of I mean here always minimum will be 0. So we try to do to the next, I mean we apply this formula to the next step. So the distance of 1 will still become 1, but the distance of 2 now can, not distance of 2, but distance of 4 can be updated, because there is a path from 0 to 1 and 1 to 4, right? So the distance of 2 will remain still infinity, but distance of 3 will also change, because we can move from 0 to 1 and then 1 to 3. So the distance of 2 to 3 will become 3, and the distance of 0 to 1 to 4 will become 0, because this path has weight 0. We have plus 1 and minus 1. So it will become 0. Now you guys understanding or still confused? I mean, I don't think you were getting.
Ma'am,
Can you
why
repeat the last step?
2 is not taken?
Sorry, what?
Distance to 2 is not taken.
Okay, distance between 2 is not clear. This graph is. Just give me 1 minute, I'll copy some other graph. Am I audible now? Hello.
Yes, ma'am.
Yes, ma'am.
So this is the example which have been discussed in the lecture. So in this example, what we did in the first step, we don't know what is the distance between, we just know what is our starting point, and we don't know what is the distance between the starting point and the every other remaining vertices. So in the first step, what we'll do, so we'll assign the distance of 0 to 0 to be 0 and all other entry to be infinity. Okay. So in the second step, what I'll do, so in the second step, I know that there is an edge between 0 to 1. So I can go from 0 to 1 using this edge, and the weight of this edge is 10. So I just assign the distance between 0 to 1 to be 10. So dv is basically the distance, okay? Distance of v. So the distance of 1 will become 10 because there is a direct edge from 0 to 1. So that's why the distance will become 10. And similarly, there is a direct edge from 0 to 7. So the distance will become 8. Okay. So this is your initial. So initial step is the distance of 0 is 0. That much you know. So from that information, you fill your first column. And from the second column, you try to use the what are the neighbors of 0. So that will gives you, that will give you the entries of second column. Okay. So in the third column, what we know, so for the third column, we have this information. We know that distance of 0 is 0. We know that distance of 1 is 10. And we know the all other entries will have distance to be infinity, but the distance of 7 is 8. Okay. So for the first step, what I'll do, so I'll try to use these distances to find out the other vertex distance. Okay. So in the third step, so I'll try to reach out from the vertex 1 to every other vertex, because we can go from 0 to 1 and 0 to 7. And 7 to 6 we can move. So that's why, we can go from 0 to 7, and from 7 to 6 we can move. So so we can apply that distance of 6 will become simply the weight of this path, which is nothing but 9. So in the next step, you observe that the distance of 6 will become 9. Okay. So in the similarly from 7 we can just we can go to 6 only, but from the 1 there is again an incoming edge to the vertex 5. So again what we'll do, so we'll update our distance of 5 to be the distance containing this path, 0 to 1 and then 1 to 5, which is nothing but 10 plus 2, which is equals to 12. So this process is happening in our third step. Okay. So yeah, so we have assigned that value to be 10. Now similarly we can, yeah, for 7 we already have that distance of 7 to be 8, right? Okay. So now we know, now we forget about these entries, whatever it is in the second step, but we will consider whatever the entries we got in the third step. Here you work step by step, and you will inform, use your information, whichever things happen in the previous step, not in the beginning, not from the beginning. So now this is my known quantity, this thing I know, and from using these quantities, I have to update my next column. Okay. So we can use the same thing. So now what happened here? I know we can go from 0 to 1 using this edge, which has weight 10. But from from the previous entry, I know that I can go from 0 to 7 using the weight, using the edge which has weight 8, and from 7 to 6 I can move using this edge, because I know now the distance of 6 from 0 is again 9. So I can use that distance, and from 6 I can go to 1 using this edge which has -4. So that's why here distance of 1 will become, using this formula, that distance of 1 becomes simply that distance of 6 minus 4, which is nothing but 9 minus 4, which is 5. So in the next step, my distance of 1 will be updated to 5. This is clear? How the distance of 1 changes from 1 to 10 to 5, because that's the main that's the main reason why we are applying this algorithm in place of Descartes algorithm, because Descartes algorithm won't change the distance which is already have been assigned to each vertex. If you apply Descartes algorithm on this set, what you will do, you always stick with the distance 10 for each vertex 1. You cannot, you won't change the distance of those vertices which are previously assigned. But in this algorithm, we can update the distance according to our entries whichever we got in the previous steps. Guys, it is clear or not?
Yes, ma'am. Yeah.
Okay. Because this is lengthy algorithm, I know.
Ma'am, why did we update the value in the fifth step from 10 to 5?
Yeah, that's why I'm saying, because initially I don't know that initially we have all the distance infinity, right? I mean,
Yeah.
in the initial stage, I cannot move in this direction. That I cannot move from 0 to 7, 7 to 6, and then from 6 to 1. Because at the initial state, I'm assuming that the distance of 6 or distance, yeah, the distance of 0 to 6 is infinity. This quantity is infinity. But as I enter in the third step, I'll get that okay, distance of 0 to 6 is not infinity, it is 9 now. So I know that this is a finite quantity, so now I can use this path to get a shortest distance path. So, and this path has a weight 5 and this edge has weight 10. So I can say that, okay, this path, I mean, this is the shortest weight path we can take. Now you understand? Because we have
Yeah.
updating the entries in the previous step. So we'll use that entries and then we will move forward.
Okay.
You try, I mean, you yourself tried.
Ma'am,
Yeah.
we have to check both directions simultaneously.
Yeah, you have to take, I mean, you have to repeat this process again and again, n times. Here we have 7 vertex, so we have to do the same process 8 times. Whatever distance you know, you just update it, use the formula that, okay, fine, we can use this path now. So the distance between 0 to 1 will change to 5. Similarly, in the next step, assume that distance of 1 will still remain same because we don't discover any other new vertex which has finite distance. But what happened? We'll update it this distance from 8 to 7 because here we can go from I mean we move to 5 using this path, that 0 to 8, 0 to 7 using the edge which has weight, I mean simply 0 to 7, 7 to 6, and then 6 to 5. But now what we can do, we can also go around this thing, right? Or we also go around this thing, or mainly, sorry, here they won't use that path. They simply use that we can go 0 to 1, now 1 to 6, and 6 to 5. Then what will be our weight? So it will be 10 minus 4 minus 1, which is 5. And we update it to be 7. So in basically, you have to update each entry in every step. This is the main reason will use this algorithm.
1 to 6, there is no edge. Right?
Yeah, there is no edge from 1 to, yeah, that's why we can assume this is the other way around. So which path they have used for reaching 5 to 7? Oh, sorry, we have updated the weight of 1 na. I mean, distance of 1 we have updated to 5. So now we can go from 0 to 1 using the weight. I mean, the weight of this path from going 0 to 1 will be 5. And from 1, I can go to 5 using the weight 2. So that's why the distance of 5 will become 7. So that's the thing. I mean, we have to use the previous steps entries to gain our next step entry. Now it is clear? You guys just try by yourself. Maybe that it will be more clear. Or we can return to this algorithm at the end of the session. Okay. I have to cover more 3 algorithms also. 7. Okay. So this is a good example for understanding this algorithm because in this example I mean at each step we are changing the values. I mean first we change this value that from 10 to 5, and then we change this value from 8 to 7, and similarly we are changing rapidly values. So this is a good example for understanding this algorithm. Okay.
Ma'am,
Yeah.
if a vertex has 2 out degrees,
Hmm.
uh, then we have to do update both values
Yeah, we
simultaneously,
have to update
or
both
we
the
have to
values.
do the consecutive steps.
Both values, because here 0 also have two vertices, now 1 and 7. So we updated both values, 1 and 7.
From 6 we have to update for 1 and 5
Yeah, from 6 we have updated from 1 and 5 also. Same thing.
in the same
Because
step.
yeah, because then only we are able to find out this path. If we don't reach to 6, then it's tough to get back to 1 using this path. And similarly, we because of 6, we can find out that the distance of 5 will become 7, because we can go from 0 to 1 via weight 5, and from 1 to, what you can say, 1 to 6 via weight -4, and then, oh sorry, this is not an edge. Yeah, but you have to update it, the neighbor of each vertex every time.
We had to update in each direction, or we have to do simultaneously for both directions.
What do you mean by both direction? I mean, you have to
Like
update the entries for
first,
each neighbors. I mean, whatever you have reached in the previous steps.
first we are going from 0 to 1 and 0 to 7.
Yeah, first we go from 0 to 1 and 0 to 7, because these are the only two out edges which are coming from 0, right? So these are the only path we can travel. In the next step, what you will do, okay, fine, I have the distance of 7, which is 8, and I have distance of 1, which is 10. Now I can move further away from 1 and 7. So from 1 and 7, I reach out to 6, and from 1, I have reached out to 5. So in the next step, I will update the entry of 6 and 5. And after that, I know we can reach out to 6 and 5, so we'll just use those neighbors, those out edges, to reach out the other unknown vertices.
Now, how to apply this formula
Oh,
in
this
this?
formula is actually not that much effective, because you can intuitively you can apply it. You can go this way, then we know these entries, then you can go to the next neighbors, and then you can, this formula simply says that here, okay, here you get that we have a distance of 1 to be, previously we have distance of 1 comma distance of, what you can say, 6 plus, no, not 6, yeah, distance of 6 plus weight of this edge, 6 to 1. So this is one example. This formula is used, that we have an edge, we have an edge 6 comma 1 belongs to E, this edge, right? So here your j will work as to be 6 and your k will work as to be 1. So you'll update your entry d1 to be the minimum of distance of 1, which we have already known to be, what we can say, 10, right? And then the distance of 6 plus the weight of this edge, 6 comma 1. And the distance of 6, which we have discovered that it is 9, I guess. Yeah, it's 9. And the weight of this edge is -4. So that's why the distance, now the minimum of this 10 and 5 will be 5, right? Minimum of these two numbers is 5. So this is how this formula will work. That for each j comma k belongs to E, in this example, we have 6 comma 1 belongs to E. We have to take the minimum of dk, because initially we know that the minimum of d1, distance of 1 is 10. So we have to take these minimum of these two guys, that 10 and 5. So we know that the minimum will be 5. And this is basically dj plus the weight of this edge, j comma k. Okay, this is a formula. Now you understood how to apply this formula? Right? Fine.
Yes,
Yes,
sir.
Okay. So now this is a single source problem. These are the two main algorithm which we use for single source problem. Now we'll go for what you can say, where we have to find out the shortest distance from every vertex to every other vertex. which is known as all pairs shortest path. You guys are familiar with the transitive closure, right? Which we denoted by A plus for any graph.
Yes, ma'am.
So we'll just try to use this transitive closure to find out the distance between every vertex to every other vertex, the shortest distance between every vertex to every other vertex. Okay. So for this, what we will do, so we'll use simple trick. We'll say that our SPK of I comma j. Okay. So these are just notation. Okay, fine. Here your K, I, and J are simply numbers between 0 to n minus 1. Whatever you have vertices, that will be your K, I, and J. So we say that SPK of I comma j, this will denote the length of the shortest path from I to j via the vertices 0 to k minus 1. I mean, this is basically the length of the shortest path from I to j using these vertices 0 to k minus 1. I mean, here we restrict ourselves that you cannot use all the vertices. We just have to use 0 to k minus vertices. And from these vertices, we have to find out what is the shortest path between I to j. Shortest path in sense of shortest weighted path, not the number of edges. Okay. So this is our notation for SPK of I comma j. So from this, we can build a matrix which is basically known as SPK. So SPK will be the matrix whose ijth entry will be SPK of I comma j. And this matrix will tell us the shortest distance between any two vertices. So we studied the adjacency matrix regarding the weighted graph. So you can SPK is basically the adjacency matrix, but we have to consider in place of one edge, because adjacency matrix, what we will do, we say that if there is an edge between I to j, we'll append it to be 1. We append that entry to be 1. But in SPK, we'll append that entry to be 1 only, entry not 1, the weight of the shortest path between I to j. So your SP0 is basically your adjacency matrix. Because adjacency SP0, what do you mean? So SP0 is nothing but the shortest path between any two vertices using only one vertex 0. So this is the only vertex you can use. So simply all the neighbors of 0 you can append to be in SP0. Okay, so SP0 will basically denote your adjacency matrix. For SP1, we will use this formula that we know that SP1 of I comma j is basically the minimum of SP0 of I comma j, or SP0 of, now here my value of k is 1, so SP0 of I comma 1 plus SP0 of 1 comma j. So you'll use this formula to get your SP1, SP2, SP3, and so on, SPN. So when you get your SPN, you know the shortest part between any two vertices using n minus 1. Seeing you after the quiz to last session. Okay. So let's do an example maybe. For this problem, we can consider this graph, because I think this is your practice problem, right? Activity question. Practice problem. This is your graph, which is already in activity questions. So here they ask you to find out what do you mean by SP0, SP1, SP3, and SP5, I guess. Okay, so SP0 is basically your adjacency matrix. These metrics actually denote the shortest path between the vertex I and j. You guys you guys gone through the videos, right? Should I explain how it works, why it is work, and all those things?
Ma'am, just summarize, please.
Okay. So basically what here we have to find out the distance between any two vertex, the shortest distance between any two pair of vertex. They have explain it using the traveling problem. That means if you are running a business, I mean, if you are a, what they say, I mean, if you are running some bus company, or you are some, they call booking manager or something, then you always have to take care of uh, the cost between any two cities, irrespective of whatever the cities. I mean, you have to take care of what is the weight between any two cities. The weight here is just the cost of cities and all things. Yeah, graph theory is a little bit hard, but it just consists of algorithms and all only. So for this problem, we try to come up with a better approach to solve such type of problems. So what we'll do, so we'll use the adjacency matrix, and uh, we use the concept of transitive closure. In transitive closure, what we'll find out that A plus will denote the, I mean, A plus actually tells us that there exists a path between any two vertex I or j or not, I to j or not, right? This is a main motive for, I mean, for calculating A plus. A plus actually tells you that if there is a path between I to j, then the entry of Aij will be 1, otherwise it will be 0. So here we know that, okay, if there is a path between I to j, A plus will give us that information. We just have to calculate the weight. Okay. So from A plus, I will go to SP0 or SPN. SPN actually tell us that SPN basically is a matrix which again contains some entries, in which each entry is basically the shortest, in each entry basically the shortest path between I to j, shortest weighted path between I to j. So SP0 actually adjacency matrix, because what happened if you want to find out the shortest path between two vertices using the simple vertex 0, then it's just a neighbor of zeros. Suppose I start with 0, so then you can only use 0 for moving to some other vertex. So that's why SP0 will be your adjacency matrix, and the other SPNs you can easily calculate using this formula. For example, in this graph, if I want to calculate what is my SP0, it's basically the adjacency matrix. You have done this question in activity question. In SPN means shortest path from I to J having number of edges. No. Shortest path between I to J where you can use any vertex. SPN will say, SPN is basically your matrix of n cross n. If you have n number of vertices, it will be a matrix of n cross n. In each entry, SPN of I comma j will simply says that it will basically the shortest distance or shortest path between I to j. This is what SPI comma j tell us. Yeah. So here we can calculate that SP0 is adjacency matrix. So adjacency matrix, for adjacency matrix, what you will do? So we'll, weighted adjacency matrix, what you will do? So if there is an edge between I to j, we'll append that entry to be that weight. Okay. For example, here I have vertices 1, 2, 3, 4. Yeah, 1, 2, 3, 4. And here I have vertex 0, 1, 2, 3, 4. So there is no edge between 0 to 0. So the distance from 0 to 0 is infinity in this case. Now again, there is only one outgoing edge from 0, which is going to 1. So that's why the distance between 0 to 1 is 1, because this is the weight of that edge. But all others are, all other vertices are of infinite distance from 0. Okay. From 1 to, again from 1, we just have two outgoing edges. So the entries will simply infinity for 0. And we have two outgoing edges which are going to 4 and 3. So the weights will be -1 and 2. And all other entry will have 0. So in this way, this is basically the weighted adjacency matrix, SP0. Now, if you want to calculate SP1, what you will do, you will apply this formula, simple formula. SP1 of I comma j because you have now sp0 of I comma j for every I and j. So just try to apply this formula and you can easily get what is your sp1 of I comma j. Yeah, it's easy. I mean, you just have to apply the formula and you can get your entries for sp1, sp2, sp3 and sp5. So when you reach out the sp5, you will get that each entry will denote what is the shortest path between any two vertices. It's a simple process. So shall I move forward or there's any doubt? I mean, if you guys gone through the video, it's easy. I mean, straightforward how to, because these are just algorithm, they work. Hello.
Ma'am,
What?
what is n? Is it the length of path?
No. N actually denotes, that's why I said na. What is N denote? That the length of shortest path using these many vertices 0 to n minus 1. So if I'm saying spn, so spn basically a matrix in which each entry spn of I comma j basically denote the weight of path. I mean basically the shortest weight of path from I to j using these vertices 0 to n minus 1. I mean basically using all the vertices. sp1 in sp1 we can use only two vertices 0 one vertex 0 because then 1 minus 1 will become 0. In sp1 we can use simple one vertex which is 0. In sp2 we can use two vertices which is 0 and 1 for going from one vertex to another, because if you want to find a path you have to go uh, tracking. I mean, you have to reach some vertex using the all other vertices, right? Right.
Yes, ma'am.
So for SP, I mean, you don't have to go through these sp1 how to calculate sp2 because it is hard. I mean, it is tough. If you want to find all the path which has its intermediate point has to be one, then it's hard. So that's why I suggest to use the formula, because the formula just contain sp0 of I comma j, which values you already know. So just put the values of I, j, k and you can get your things. So the formula will easily compute what is your matrix sp1, sp2, sp3, and at the end sp5 will give you all the answers of shortest paths. Okay. Now, shall I go to next algorithm or spend so much time in this? Okay, let's discuss two other algorithm. Then we are almost done. So after that, we'll come back to these two. Okay. So now we'll come back to the notion of trees. You know that trees are basically acyclic connected graph. This is what we mean by tree. And there is another term which is called as spanning tree. So spanning tree is basically a tree which cover all the vertices. Tree which cover all the vertices. And we know that the spanning tree in any connected graph need not to be unique. For example, if you have this type of graph, we have vertices 1, 2, 3, 4, 5, then you can say that your this is your one spanning tree which move from 1 to 2 to 5 to 3 to 4. This is spanning tree because it is a tree since it is connected and it is acyclic. So it is a tree and it is covering all the vertices. So that's why it is a spanning tree. So the other spanning tree could be this one. That 1 to 2 to 3 to 4 to 5. I'm just looking about the minimum spanning tree. What's Prime's algorithm. Yeah, we'll discuss Prime's algorithm and Kushal's algorithm, both of the things. So this is the this is the what you can say definition of spanning tree, and the spanning tree is not unique in any graph. So for finding the shortest, finding the what do you say, the shortest spanning tree? Shortest spanning tree means the spanning tree which has weight minimum. Sorry, minimum spanning tree. Minimum cost spanning tree, which we denoted by minimum cost spanning tree. So for finding minimum cost spanning tree, MCS. So for this, we have two algorithms. First is known as Prime's algorithms, and second is Kushal's algorithm. So we'll discuss this two algorithm. So you guys familiar with the definition of minimum cost spanning tree? Basically a spanning tree which has minimum cost. For example, if I'll append the weight on this graph, let's say 2, 4, 5, 6, 7, 8, and 9, then the cost of this spanning tree will be just addition of the cost of every edge. So this edge has weight 2, this edge has weight 5, and then we have weight 7 and 9. So the weight of the spanning tree is basically 2 plus 5 plus 9 plus 7, right? And similarly, the weight of the spanning tree will be something else. So we have to find out that we have so many spanning tree. So which is the spanning tree which has weight minimum, is known as minimum cost spanning tree. So there are three main basic properties of tree. That if we have a tree of n vertices, then it has n minus 1 edges, and it will be acyclic, which is the definition itself, and connected also. But there is one more property, that for each vertex u and v, there is a unique path. Unique path from u to v. This property need not it won't hold in general graph, but in case of tree, it will hold. For example, if you want to go from a vertex u to v, you have just only one single path in tree, and that will be unique. Yeah, that for each vertex u and v, we have a single path and which is unique. So these are the basic properties of tree, which we already discussed, I guess.
Ma'am, U and V being vertices of same edge or different edge?
Vertices of which edge? Sorry. Yeah, there are some in
Any two
between
vertices.
vertices. Yeah, there are in between vertices, but the path will be always unique. In case of tree, if you have a tree, then you have a unique path from every vertex to every other vertex. So the Prim's algorithm actually work in the using the fact that if you have a graph, you try to grow a tree from that graph. For example, if you have this graph, which has been discussed in the video, or we can take some other graph. Suppose this is your graph. And this graph has vertices, let's say 0, 1, 2, 3, 4, and 5. And we have weight append on it to be, let's say 10, 6, 5, 8, 20, 30, 2, and 1. So what does Prim's algorithm says? Prim's algorithm says that pick an edge which has minimum weight. So in this case, the edge 4 to 3 has the minimum weight, right? So we pick this edge from 4 to 3, and this has minimum weight 1. Now the Prim's algorithm says that, okay, now add those edges which will connect this some known vertices to unknown vertices, which was obviously of minimum weight and which doesn't create any cycle. So in this case, I have an edge 2 which adjacent to 3 and going to 2, since 2 is our new vertex, so we can append this edge, because again it is minimum weight and it is going from a vertex which you already know to a vertex which we don't know. So basically what we are doing, we are growing our tree. I mean, we start with this edge which cover 4 and 3, and which has minimum weight 1. Then we append an edge which has minimum weight and which will cover some unknown vertex. In this case, the 2 vertex is unknown for us, so we add this edge. And now again we can do the same thing for 2. So from 2 we have 2 edges coming out. One is which has weight 8 and the other one which has weight 30. So obviously we have to choose the minimum cost edge, so we'll choose this edge which going to 1 and it has weight 8. Okay, now similar thing we can do for 1. So from 1 again we have 2 edges which has weight 5 and 20. So we basically take the edge which has minimum weight, so we can take 5, and once we cover all other vertex, all of the vertices will stop our process. But here we again we haven't covered this vertex 5, so we also have to attach one more edge. So the edge which coming out from 0 to vertex 5 and has minimum weight is basically one edge which has weight 6. So this is your minimum spanning tree which will be given by the Prim's algorithm. So Prim's algorithm basically says that select an edge which has minimum cost, and then append all those edges which has minimum cost and which won't create a cycle. For example, in this case, if suppose this edge, if this edge weight 1, so if I want to append an edge from 2, so we cannot use this edge which has weight 1, because if we append this edge, then we create a cycle. But in tree we don't need a cycle. So basically we want those edges which won't form a cycle and which will of the minimum weight. It's basically removing edge from max. Yeah, this will be the Kushal's algorithm. Kushal's algorithm says that. Okay, fine, you can say that. But this is the main process of algorithm. Just select an edge which has minimum weight, and then obviously, as we do all the other algorithm, repeat the same process for every other vertex. This is known as Prim's algorithm. Is any doubt on this?
No, ma'am.
Yeah, it's easy. And basically it actually work on the what we call the minimum separation lemma. So basically the minimum separation lemma tell us that if we have a graph which can be decomposed into two disjoint sets, suppose these are disjoints, and if we have an edge which connected to these two edges E, then this edge obviously belong to the spanning tree. This is your minimum separation lemma, which already have been covered in lectures. So you can have a look at it. It's simple. I mean, it basically says that if you have two components which disjoint your graph, then if there is an edge between these two components, since we are working in a connected graph, there should be an edge between these two components. So that edge will always belong to the minimum spanning tree. And if there are more than one edges, then we will select the minimum cost edge, and that minimum cost edge will also belong to the spanning tree. So this is known as minimum separation lemma. In the on only using this lemma, we can show that the Prim's algorithm is workable. Okay. Now the next thing is Pushkal's algorithm. So Kruskal's algorithm actually work in the opposite way. For example, if you have this same graph, then what does Pushkal's algorithm says that in place of taking a minimum edge, we can take any edge which has a minimum cost and which does not create a cycle. In Kushkal's algorithm, firstly, we'll say that my whole graph is disconnected. I mean, you just take all the vertices as they are placed. Now you try to add those edges in between vertices. I mean, those edges which are minimum cost and which cannot create a cycle. So in the whole graph, I have this minimum edge or this minimum edge because both has weight same. So let's say this is our 3. So that it won't be this. Okay. So first what I'll do, so I'll append the edge which has minimum cost. So my vertices are looking like 1, 2, 3, 4, 5, 6. So I'll append this edge. Now this edge will connect two components of the graph, basically the vertex 2 and 4. In the next step, what I'll do, so I'll find out that edge which has minimum cost and which won't create a cycle for us. So it's easy to see that this is the required edge. So we'll append this and we get we also attach a vertex basically to a tree. I mean, we are reducing the number of components which we want. At start, we have 5 vertices which are disconnected. Now we have 3 vertices which are connected. Basically, you can say that 4, 2, and 3. Now 4, 2, and 3 are connected and all other are disconnected. So we'll try to find another edge which has minimum weight and which won't create a cycle for us. Now here you can observe that we have these edges. So this is 8, 2, 3, 1, 10, 6, 20, and 5. Right? Now this edge has minimum weight among all the edges which haven't assigned to a tree. But if I attach this edge, then I can get a cycle. But in a tree, I know that I don't want a cycle. So we won't take this edge. In place of it, we'll find out the some other minimum cost edge which won't create a cycle, which is basically the edge between 0 to 1. So I'll assign that edge between 0 to 1, which is of the weight 5. And we proceed in the similar way. So again, we find out the minimum cost edge, which is 6 to, what is this, 0 to 5. And again, the minimum cost edge is this one. This is it. So you observe that in the Kushal's algorithm and the Prim's algorithm, whatever we get the spanning tree, both are different. The spanning tree and the spanning tree is different. So there is no uniqueness in spanning trees based on the algorithm also, because there may be choices you have to make. For example, if we have these 3 edges of the same weight, then you can choose any one of them and you can append any one of them. So that's why there is no unique spanning tree, but there is a unique minimum cost spanning tree. I mean, you can compute the cost of both of the spanning tree, it will be the minimum thing. So this is known as Pushkal's algorithm, which is used for finding out what is the minimum cost spanning tree. So these are the main basic algorithms which you need: Prim's algorithm and Pushkal's algorithm. These are not same spanning tree, but the weight of those two spanning tree have different weights. Because we have changed the weight here now. I mean, I replaced this weight by 1. So that's why they are different weights. I mean, I take the similar graph, but I change the weight of edges. Here the weight of edge will be 1. Okay. Replace it. And the previous example, I have this entry to be 1, not 3. So that's why they both are different weight, coming to be different. Okay. Now we can have little bit, some questions. So if I'll say that find the minimum cost spanning tree in the following graph. What will be your answer? Suppose this is your graph. Initialize with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we will assign a weight on each vertex to be 8, 7, 6, 2, 1, 10, 20, 3, 23, 35, 50, 50. Suppose this is your graph, then if you want to find out what is the cost of, because minimum cost penalty could be different, but the cost will be the same. So what is the cost of minimum cost spanning tree? So what should be your answer? You can easily solve it, just 1 minute question. One 38. Yeah, I think so. One 30. Yeah, whatever it is. So shall we solve it? Yeah, okay, fine. Okay, so basic process is you can use any of the algorithm. It's not, I mean, it's not pile, it's that insect which make the sound. So first what we'll do, so we'll select the minimum cost edge. So in our graph, the minimum cost edge will be this, the one, right? There is no other edge which has minimum cost, right? So select this edge. So we'll append, and this will cover our vertices 4 and 2. I'm using Prim's algorithm that we have to grow our tree accordingly. Okay. So from here, I have to move from 2 or 4, whatever you will choose. So from 2, I have 3 edges, which has weight 2, 7, and 50. So again, I have to select that edge, which cannot create a cycle, and which will assign to some new vertex also. So here we have this edge, which is of minimum cost 2, and it will assign us the new vertex 3, and it also won't create a cycle, right? Now from 3, I can go to 6, and from 2, yeah. So from 3, I can go to 6 because there is only one edge. So this edge will also contribute to our, what we can say, spanning tree, which cost 6. And similarly, I can go from 0 to 1 using the edge 8, but I also I mean, we can also apply this edge 7, which is going from 0 to 2, and which will cover the vertex 1, because this is again a minimum, because it has cost less than that edge, which we already want to assign. If we assign this edge 0 to 1, which has cost 8, then it will increase our cost in spanning tree. But we want minimum cost spanning tree. So that's why we have to assign this edge from 2 to 1. Okay. Now there is no other edge for connecting these two components. We have to assign these two edges. So that means we have to assign this edge 50, which has weight 50 for connecting these two components. So in this component, we will find what is the minimum cost edges, which won't create a cycle. So it's clearly we can go from 9 to 8 and from 8 to 7 using these two edges, 35 and 23. Right? And similarly, we can do same thing for this cycle also. So we'll select those two edges which of the minimum cost, which are simply the edges from 4 to 5 and 5 to 6, and the cost will be 3 and 10. So this is our required spanning tree. You can calculate it. It will be whatever the answer is. This is the thing you have getting, right?
Yes,
Any
ma'am.
doubt in this question?
No,
No.
ma'am, it's clear.
Now let me go to next question. Just take time to solve this question. It's based on the Descartes algorithm. All this is already discussed or something else? Does this question already have been discussed? I mean, okay, it's an activity question. Then okay, fine, we can discuss some other question. Okay, this has already been discussed, so you can solve this question. Yeah, the answer is B, correct. Because what we will do, so in this question, what we'll do, so we'll try to find out the path which won't use this x. So suppose we don't have this x. So then we travel from this path. And what I want this shortest distance to be less than 13. So you can observe that when you travel from this using this path, that you go from here, then here, then here, and then here, here, and here. Then according to this part, you will get the distance of this part to be 13. And you want your x to be such a way that the shortest path from vertex A to J is less than 13. So what you will do, so you can simply say that your x will be less than 7, because the these two edges will contribute the weight 7. So if you don't want to use this edges, then the value of x should be less than 7. So this is basic idea of the proof. We can solve this question based on the prime solver. Previous one is similar to graded assignment. Okay. is this graded assignment question? Actually, we don't know about the question. The questions have been given to us already for creating solve with us. But it's okay. Fine. Don't worry. One question won't change your grade. Just answer. Okay, I won't discuss it. Let's say. And maybe all other questions are also from graded assignment, I think. Don't answer this answer of this question in the chat box, okay? You guys just discussed. Okay, previous one or this one, this question 3.1 or this one, question 1. Okay, previous one. It's okay, fine. Answer this question. You have to find a sequence when we apply Prim's algorithm in the given adjacency matrix. Suppose these are vertices 0, 1, 2, 3, 4, 5, 6. 0, and you can notice here. See, yes. Okay, fine, don't worry now, answer what we can do. Actually, I also don't know that these questions belong to graded assignment. Someone just give us questions to discuss in the class. So we prepare those questions and we will explain to you guys. I don't know that this is from graded assignment. It's not my fault. Yeah, I will understand it. I will explain it. Actually, we want to find out a sequence. If we apply Prim's algorithm on this graph, which will denoted by this matrices. So that's why I have assigned what are the vertices. So we have 7 vertices, namely 0, 1, 2, 3, 4, 5, 6, right? And you have to give a sequence of vertices when you apply Prim's algorithm onto this graph. Oh, this is fine. The vertices is given to be PQRSTUV. Yeah, so you can use that, or you can use this thing 0, 1, 2, 3. PQ. Yeah, I think so. Yeah, 0 means no edges. That's why 0 stands. You can have time. So shall we discuss now? I mean, it's enough. Okay. So basically what we'll do, so we will construct our graph using this adjacency matrix, and then we will apply our algorithm onto this graph and we'll get our sequence. So we have vertices, namely, let's suppose this is P, Q, R, S, T, U, V. Suppose these are my vertices. Then I append the edges according to my adjacency matrix. So there is an edge between P to Q, which has weight 6. So there is an edge between P to Q, which has weight 6. So this is not a directed graph, because you can simply say that this matrix is symmetric. So whenever we have a symmetric matrix, the graph will be undirected graph. So this is a symmetric matrix, so our graph will be undirected graph. So there is an edge between P to Q, which has weight 6. Now there is no edge between P to R, not for P to S. P to T, we have an edge which has weight 9. Now we have an edge from P to V. Okay, so fine, we can append it. P to V, we have an edge which has a weight 7. Similarly, we from Q to S, we have an edge which has weight 8. From Q, we don't have any other edge. From R, we have an edge to U, which has weight 1. And from R, I have an edge up to V, which has an weight 3. Okay. Now, again, from S I have an edge to T which has weight 2. So I'll assign a edge here and I'll assign the weight, and then we don't have any edge. And from T also, and from U to B we have an edge which has weight 5. So I think this will be the graph representing the given adjacency matrix, right? You guys also got this graph or any other correction? Now we will apply Prim's algorithm here. So what we'll do, so we'll select our minimum cost edge and we'll append all those edges according to them. So here obviously this is our minimum cost edge. So we have to select this edge. Yeah. So our first choice of vertices will be R and U. And after that from R and U, I'll select V because this edge have been covered. Now I'll select this edge. So then after this I have V, and from V I cannot select this edge which is of weight 5 because it will create a cycle. So I'll select the vertex P and this edge. Now after P I have two choices. I can select this edge which has weight 9 or this edge which has weight 6 because both of them are not creating cycles. So I'll select this, the second one. And here also I can select this edge also to complete my minimal spanning tree. So the last vertex which have been selected will be S. So maybe this is your sequence, R, U, V, P, Q, S. Any doubt?
No, ma'am.
Okay. So I think I should not discuss any other question. पता चला वो भी practice assignment से graded assignment से. You guys have any doubt? So we can discuss them. I have questions, but I won't discuss. First, I have to confirm. Yeah. Okay. So here, your week 11 will be completed. I mean, according to theory, you may have a session for practice. No, we cannot say. Also, we don't have that much time. We just have 10 minutes. It's best. We can do it on next session.
Ma'am, do we have open session 3 also for this
We
week?
will see because we haven't discussed any question till now. When will your exam? I mean, end term?
Ma'am, Warshall's algorithm
28.
is not being discussed.
Yeah. So we'll try to have some sessions on graph theory itself because we will discuss so less question on graph theory.
Floyd Warshall is also left.
Sorry, what?
I'm saying Warshall's algorithm is left.
Oh, Warshall's algorithm.
Yeah.
But that will be the part of what we can say transitive closure. Warshall's algorithm is a part of transitive closure, I think so. I thought Vishal sir have
Floyd.
covered it.
Oh no.
Yeah, there is a T here.
Vishal sir covered till Dijkstra's algorithm.
But Warshall's algorithm are ahead of Dijkstra's algorithm, no?
Yeah.
Okay, we'll discuss in the next class. Okay. So shall we end this session here?
There is
I'll share the notes.
Floyd Warshall algorithm also.
Which one?
Floyd Warshall.
Deployed version is that SPN wala. I mean, we have discussed this na SP1, SP2, SP3. This is the Floyd Warshall algorithm, right? The name will be different maybe. You'll just read out if you have any doubt on that algorithm. We'll discuss in the next one. Andrew sir is not a principal, but yeah, he's the head of this program. Yeah, my LinkedIn profile is on my name, Samiksha Lunkar itself. You can search. Okay, you can ask Anjali whatever your doubt. Either you send a screenshot or I mean, you can simply say what is the question. Last two question. Okay, this is a question on based on planar graph. So what you will do, in place of 1, 2, 3, you just take colors red, blue, and green, whatever, and color the graph accordingly. I'm audible, right?
Yes.
So in this
Yep.
question, what you will do, in place of 1, 2, 3, just take a color red, blue, green, or whatever you want, and then try to assign an edge. And you know that two adjacent vertices cannot have an what you can say same color. So this will be the approach for solving this question. And by planar graph, you mean there is no cross edges. So, for example,
Ma'am, screen is not visible.
yeah, I haven't shared. Wait. So, by meaning of a planar graph, we mean such type of graph. You see that this, you think it is not a planar graph because the edges are crossed. But the same graph we can draw in this way. No, but if I'll take in this way, then also the edges will cross. So the planar graph is basically those graph in which your edges should not crossed. This thing should not happen. So when you assign every vertex to a color, try to add such type of edge which won't cross in this way. Then you might get your answer easily. You got what is the idea? I mean, you have to use two fact. The planar graph is basically the graph which can be drawn in this way ki, not two edges will collapse which have some intersection point. For example, this graph we cannot draw in such a way that both edges won't intersect, because if I want this edge to go here, I want, but we can do this thing. Yeah, this is a planar graph. Here these two vertices are connected, and we'll just stretch this edge to be in this way. So now this type of graph is known as planar graph, which can be, I mean, you just have to modify it in such a way that the edges won't be intersect to each other. So such is known as planar graph. So use these two definition, you will get your answer. It's not that much difficult questions. It's ninth one, and which one last? Yeah, second coloring graph. You just have to find out what is the possible coloring of this graph. It's stated so vastly, but basically you just have to find out what is the possible coloring of that graph. That will give you an answer. Just try it out. Otherwise, I will fully discuss. Okay, so can we end this session here? I mean, if you guys don't have any doubt. Okay, then I'll
Thanks, ma'am.
end
Bye.
this.
Good night.
Yeah, thank you. I mean, today's session is not that much helpful, but yeah, fine. Yeah, it's hard. Actually, I haven't told to discuss theory. They just told me, okay, I haven't finished. So you first discuss theory, then we will discuss question. So that's why I got confused a little. Fine. Yeah, it is hard little bit. Okay. Fine. So good night, everyone. I'll stop here.
Ma'am,
Yeah.
um, uh, can we practice graph theory from NCERT books, or
Graph theory
can
haven't
you
covered in
recommend
NCERT
any?
books, I guess.
Okay.
For graph theory, there is a book. Just wait a second, I'll share the book also. It's a pretty standard book. So many people use this book.
I think graph theory is not in NCRT book.
Yeah, it is not an NCERT book because it's a graduate level course. So it won't be an NCERT book.
Yeah, ma'am.
I'll share a book for graph theory. It is a pretty standard book. It's so many people used. It's called B West. I guess you guys also know.
Ma'am, can you repeat?
B West, Introduction to Graph Theory by West.
B West. Okay, ma'am.
Yeah, I'll share the PDF itself. I have PDF. But in this book, you have so many topics, so I don't think. I mean, this book contain everything in detail with proof, with the explanation, with examples and all. And it's so standard book, so it will be tough to read such kind of book. So let's try. Yeah, I have shared the PDF.
Ma'am, in exams, questions will be easy, medium
No. Question won't be
from
from
graph
this
theory.
PDF. Okay. This is for your own interest. If you want to make yourself comfortable in graph theory, then you can solve these questions and all, because this book contain so standard question. I mean, it's not easy to solve it, as this is MSc level book. So just try to read it. I mean, it will contain some basic graph theory, for example, trees, spanning trees, vertex cover, independent sets and all, but it's pretty hard.
In exams, questions will be simple or
Yeah, it will be simple. I
like
mean, question will be of not that much simple. You can say that like practice as assignment question. In practices, if you are able to solve your graded assignment 60%, then 90% question you can solve one question in exam. So
Ma'am, can we discuss some questions from this book?
no, actually it's a so standard book. I don't think there are simple questions. This book is I'm giving you, if you have interest in graph theory, you can read first chapter itself only. First chapter will contain basic graph theory, motivations of graph theory, and the second chapter will contain trees, spanning trees and all. But all other chapters are so tough, or it's not that much worth it. The first two chapter you can read it and make yourself comfortable.
Okay, ma'am, thanks for the book.
ma'am, how many weeks takes for this book?
How many?
How many weeks?
Actually, this book is used for particular two MSc courses. So you can think about how many days it will take to complete this book. And you just
I
have a
think
look.
not days, maybe months.
Yeah, maybe. Yeah, Königsberg bridge problem is one of the ancient problem which actually give birth to the graph theory, mainly the path connectedness and all things. That there are 7 bridges connecting the whole city, and you cannot go from one component to other or you cannot travel some component. I mean, such type of problem is known as Eulerian path problem. Yeah. These all things are contained in this book. If you want, you can have a look. Eulerian graph, Eulerian paths, Eulerian cycles.
Ma'am, do we get basic questions
Basic
or
questions of graph
beginner
theory.
level questions for practice purpose? Yeah.
Okay, so I'll try to give it. I mean, I don't have it now.
Uh, you said in this book there are direct
Yeah, there will be
standard
difficult
questions,
question, but there are some solved examples. So, and the theory is good, so you can have a look. I will
but
try to give some. I mean,
for the fact practice purposes, you would like to start with the basic questions.
yeah,
Uh,
for practice purpose, I will try to find some PDF. I mean, try to find some book. I don't have it now. Okay, so I'll end this session here. Okay, we'll meet in the next session. Good night.